Astronomers use sophisticated methods to detect exoplanets, planets orbiting stars outside our solar system. One of the most popular methods is the transit method, in which astronomers look for tiny droplets in a star's glow. When a planet passes in front of its host star from our vantage point on Earth, it temporarily blocks out part of the star's moon. By observing changes in brightness over time, astronomers can determine the size of the planet and its orbital period. Another popular method is the ray velocity method, also known as the Doppler method. This approach is based on a planet's influence on its star. When the planets revolve around each other's forces cause the star to wobble slightly. This wobble can be detected by the change in the star's light spectrum. When a star moves toward us, the moon appears blue, and when it moves away, it turns red. By measuring these motions, astronomers can determine the position and mass of a planet. Direct imaging is another fascinating method, although it is more difficult due to the brightness of stars outshining their planets. Astronomers use advanced techniques such as coronagraphy and adaptive optics to block out the star's light, while capturing the light reflected or emitted by the exoplanet. This technique is particularly useful for observing large planets far from their stars, providing insight into their atmospheres and potential habitability. Gravitational microlensing is a more modern technique that uses light bending around massive objects such as stars. When a foreground star passes in front of a more distant star, its gravity can magnify the light of the distant star. If the foreground star has an exoplanet, distinct features appear on the light curve indicating the planet's presence. These techniques allow astronomers to detect planets that are otherwise too dim or distant to observe by other methods. As technology advances, these methods will continue to be refined, expanding our ability to explore the diverse worlds of the universe. Determining the potential habitability of exoplanets involves a comprehensive analysis of the various environmental factors that could support life as we know it. One of the main criteria for habitability is the concept of the habitable zone, often referred to as the Goldilocks zone. This is a region around the star suitable for the presence of liquid water on the planet's surface. Because water is essential for life, detecting exoplanets in this region is an important step in assessing their ability to support life. Beyond space, the composition of a planet's atmosphere plays an important role in its habitability. Astronomers are studying atmospheric gases that could create a stable climate that supports liquid water. Data on the presence of molecules such as carbon dioxide, oxygen, and methane can be used to identify global biological signatures. Instruments on spacecraft and ground-based observatories analyze light spectra to detect these gases, giving scientists clues about the planet's atmospheric conditions and any processes that might indicate biological activity. Geologic features also contribute to our understanding of habitability. For example, the presence of plate tectonics can promote nutrient recycling and a dynamic climate that may be favorable for life. Assessing conditions on the planet's surface, such as temperature, pressure, and geologic activity, helps scientists predict whether these conditions can support the development of living organisms. In addition, recent advances in astrobiology have led researchers to consider alternative life forms that may not depend on water as we know it. For example, some hypotheses consider the possibility of life based on ammonia or even silicon. As the search for exoplanets continues with modern technology, our understanding of habitability may expand to encompass a wider range of environments, thereby contributing to the search for life beyond Earth. Several exoplanets have emerged as the most promising candidates for potential life as we know it. Among the most notable is Proxima Centauri b, which orbits the red dwarf star Proxima Centauri, our nearest stellar neighbor. Located in the habitable zone, this planet has conditions that could allow liquid water to exist on its surface. However, the proximity of a blazing star affects the protection and longevity of the atmosphere. Another attractive competitor is Kepler 186f, located in the Kepler 186 system. This planet is the first Earth-sized planet discovered in the habitable zone of a star similar to our Sun. Its size and location indicate that it has good water conditions, and is therefore an interesting object for further study. Observations of its atmosphere and surface properties may explain its ability to support life. Above is TRAPPIST-1, a system of 7 Earth-sized planets orbiting a cold dwarf. 3 of these planets are in the habitable zone of the star, meaning the temperature is ideal for liquid water. The diversity of these planets opens up many ways to study different aspects of nature that can expand our understanding of life and what sustains life. Finally, LHS 1140b is another giant planet of interest to scientists. Super-Earth lies in the habitable zone of its star, and its size is important, which may indicate the nature of its atmosphere and its ability to absorb heat. In addition, its relative proximity to Earth allows for more detailed observations with existing and developing telescopes. Each of these exoplanets provides unique opportunities to study conditions favorable for life and expands the boundaries of our understanding of what might support biological activity in the universe. Compared to our solar system, exoplanet systems show an amazing variety of planet types, orbits, and dynamics that challenge our understanding of planet formation. One of the most striking differences is the predominance of hot Jupiters, gas giants orbiting very close to their host stars. In contrast, the gas giants of our solar system, such as Jupiter and Saturn, lie much farther from the Sun. These close-orbiting gas giants have likely migrated inward toward the planet over time due to gravitational interactions, changing our ideas about the stability of planetary orbits. In addition, the arrangement of planets in many exoplanet systems can differ significantly from the patterns observed in our solar system. In some systems, multiple planets have been found in tight orbits, resulting in configurations that are much more compact than in our solar system. In some cases, researchers have observed systems with closely spaced planets that exhibit resonant orbits, where the gravitational interaction between them creates a rhythmic motion pattern. This arrangement can lead to dynamical interactions that are not normally observed between planets in our solar system. The composition of exoplanets also varies greatly. While our solar system contains terrestrial planets such as Earth and Mars and gas giants, many discovered exoplanets, particularly super-Earths and mini-Neptunes, vary in size and atmospheric characteristics. These planets may have unique characteristics such as thick hydrogen-helium atmospheres or rocky compositions that have no direct correspondence with any of the planets in our solar system. This variability allows researchers to propose new hypotheses about the formation of planets and the factors that influence their evolution. Finally, the prevalence of planetary systems around different types of stars adds another layer of diversity. Many exoplanet systems are around M-type red dwarfs, which are abundant in the galaxy, but they have different temperatures and luminosities compared to our Sun. These differences affect the habitable zones and potential climate of planets orbiting these stars. By studying these differences, scientists can gain important insights into the processes that form planetary systems and the possibility of life beyond Earth. The Fermi paradox points to an apparent contradiction between the high probability of extraterrestrial civilizations in the universe and the lack of evidence for the existence of such civilizations or contact with them. The paradox, named after physicist Enrico Fermi, is often expressed as the question, "Where is everyone?" Since there are billions of possible planets in our galaxy alone, it is safe to assume that we have found signs of intelligent life. But despite decades of searching, no clear evidence has ever been found. Many solutions attempt to explain this paradox. One possibility is that intelligent life on Earth is very rare. Although many planets are ideal for life, the transition from simple organisms to complex organisms and finally to evolved planets is a unique phenomenon or a very rare event in the history of the universe. This idea suggests that while microbial life may be common, technologically advanced civilizations may be few. Another solution suggests that advanced civilizations usually self-destruct before reaching the stage where they can communicate through space. This concept, often called the Great Filter, assumes that there are significant difficulties or catastrophic events, such as nuclear war, ecological collapse, or technological disasters, that prevent civilizations from surviving long enough to explore or colonize the galaxy. If this filter occurs at different stages of civilization, this could explain the silence we observe. Alternatively, some theorists suggest that advanced extraterrestrial civilizations exist but actively choose not to make contact with humanity. This could be for a variety of reasons, including a desire to avoid interference from less advanced civilizations, or a belief that detecting their presence would disrupt the natural development of nascent species. This speculative position is consistent with concepts such as the prime directive in science fiction, suggesting that there is some kind of cosmic code of ethics preventing contact with less advanced life forms. Finally, some hypotheses suggest that we may be overlooking signs of extraterrestrial life. Advanced civilizations may be using technologies or methods of communication that we are not yet able to detect. It is also possible that extraterrestrial civilizations exist in forms or conditions radically different from life as we understand it. As our understanding of the universe and technology continues to grow, the search for extraterrestrial intelligence may reveal new aspects of the Fermi paradox and the possibility of further exploration of things lost in our world. Life that develops on planets orbiting red dwarfs may have unique characteristics due to the unique environmental conditions associated with these stars. Red dwarfs are the most common type of star in the universe, accounting for 75% of all stars. They are cooler and dimmer than massive stars such as our Sun, so they are closer to the star. This proximity opens up many marvelous possibilities for the development of life. An important aspect is the influence of astrology. Red dwarfs are known for their starbursts and magnetic activity that can blanket nearby planets with radiation. If a planet were to approach a red dwarf in its habitable zone, its atmosphere would collapse, making it difficult for life to develop. But life can adapt to these conditions and develop defense mechanisms against harmful radiation. For example, organisms can build thick protective layers or biochemical pathways that reduce exposure to radiation. And planets orbiting red dwarfs are represented by a tidal lock. This means that a planet can rotate on its axis so that one side always faces the star, while the other side remains in infinite darkness. The open side is very hot, and the dark side is cold. Life, if it arose on such planets, could adapt to survive at such extreme rates. This could lead to the development of unique biomes in the evening zone, where temperature, light, and heat transfer are more favorable to support the development of different life forms. In addition, the possibility of liquid water on such planets greatly increases the chances of life. Even if the planet is locked in a tidal zone, water could remain in a liquid state at the boundary between the light and dark sides, creating a suitable environment for life to evolve. Such a scenario could have allowed organisms highly specialized for their niches to evolve, resulting in diverse ecosystems adapted to different conditions. Although the environment around red dwarf stars presents unique challenges, the possibility for life to arise still exists. Evolution can lead to organisms with specific adaptations to radiation, temperature extremes, and niche availability. Exploring such possibilities expands our understanding of the resilience and adaptability of life, broadening the horizons of where and how life can exist beyond our solar system. Biosignatures are indicators or evidence of the existence of life in the past or present, especially in the context of exoplanets. These signatures could take many forms, including specific molecules, atmospheric patterns, or even surface features that indicate biological activity. The search for biosignatures is a fundamental aspect of astrobiology because it helps scientists identify planets that may have life or that have supported life in their history. One of the key methods for detecting biosignatures is spectroscopy, which involves analyzing the spectra of light emitted or absorbed by a planet's atmosphere. When starlight passes through a planet's atmosphere, certain wavelengths of light are absorbed by specific molecules present in the atmosphere, creating a unique spectral fingerprint. By studying these fingerprints, researchers can detect gases that are often associated with biological processes, such as oxygen, methane, nitrous oxide, and ozone. The simultaneous presence of these gases, especially if they originate from biological sources, can provide strong evidence for the existence of life. Modern telescopes, both ground-based and space-based, are equipped with highly sensitive spectrometers that enable such analyses. Future missions, such as the James Webb Space Telescope, are designed with the ability to analyze the atmospheres of exoplanets, especially those in the habitable zones of their stars. These observations can provide crucial data on temperature, pressure, and chemical composition that can identify potential biosignatures. Another approach is to analyze surface features such as signs of vegetation and carbon dioxide. For example, the presence of chlorophyll-like molecules may indicate the presence of photosynthetic life like that found on Earth. In addition, changes in surface color or texture indicate biological processes that distinguish geologic features. Despite the methods used to identify biomarkers, interpretation of these data is difficult. Signatures may arise from abiotic processes that contradict the findings of spectral or surface analysis. Researchers must therefore approach the examination of evidence with caution, often requiring multiple lines of evidence to support the idea that there is life on an exoplanet. As technology advances and understanding of biosignatures increases, the search for life beyond Earth is likely to become more nuanced, opening new avenues for exploration and discovery in space. The formation of exoplanets usually begins in the protoplanetary disk, a rotating disk of gas and dust surrounding a young star. This process begins when material in the disk begins to coalesce due to gravitational forces, forming solid particles that collide and stick together. Over time, these particles combine to form larger bodies, eventually forming planetesimals that can be several kilometers in size. When these dwarf planets collide and merge, they eventually become protoplanets. When a protoplanet reaches a certain size, the gravitational pull becomes stronger, pulling more material from the surrounding disk. This phase leads to the formation of gas vents, where the protoplanet collects large amounts of gas, mostly hydrogen and helium, from the disk. In contrast, terrestrial group planets such as Earth are mostly rocky, with the remaining gas contained in a thin atmosphere. Migration is a crucial factor in the evolution of exoplanets. Many planets move away from their original location. This is affected by interactions in the protoplanetary disk. When a planet appears, it creates a perturbation in the disk, affecting the distribution of gas and dust around it. These perturbations can transmit angular momentum, causing the planet to fall inward toward the star or outward toward the colder regions of the disk. The normal migration process, known as Type 1 migration, occurs on most small planets, such as Earth-sized planets, when they interact with the disk atmosphere. Larger planets may experience a different type of declination as they travel through the disk and experience significant motions toward the star. Another factor is the density of the disk. If the disk becomes less dense over time, the gravitational interactions that favor migration may change, leading to stability of some planets and a significant shift in the position of others. These migration processes can lead to unique configurations in exoplanetary systems. For example, the existence of hot Jupiters, gas giants found very close to their stars, suggests that they likely migrated inward after forming in the colder regions of their protoplanetary disks. Understanding how exoplanets form and migrate enriches our knowledge of their characteristics and orbits, helping researchers piece together the different histories that form the diverse planetary systems we observe today. Proposed methods for interstellar communication with potential alien civilizations include many innovative approaches that reflect both our technological capabilities and our understanding of how intelligent life can transmit information across vast cosmic distances. One of the simplest methods is the use of radio waves. This concept is being actively pursued by projects such as the Search for Extraterrestrial Intelligence, or SETI. By transmitting and listening for radio signals in certain frequency bands, especially those commonly associated with intelligent communication, humanity is looking for signs of extraterrestrial activity. Another method involves transmitting laser beams, which can be very directional and potentially travel vast distances with minimal scattering. Using powerful laser pulses, scientists have hypothesized that these signals could be directed toward nearby star systems. Laser communication can be considered a more efficient method than radio waves due to its narrower focus and reduced noise interference in space. If civilization manages to detect such signals, the potential for two-way communication could be greatly expanded. The concept of sending physical probes or spacecraft to neighboring star systems is also gaining attention. While this idea is limited by current technology, it involves using advanced propulsion systems to send small, unmanned spacecraft equipped with communications instruments. These probes could transmit data back to Earth and perhaps even carry messages intended for intelligent civilizations they might encounter. Initiatives such as Breakthrough Starshot aim to develop the technology to send tiny, lightweight probes to nearby stars at several times the speed of light, allowing direct exploration and communication. Finally, there is the possibility of encoding messages in astronomical phenomena, for example, using signals generated by pulses. Rotating neutron stars regularly emit radio pulses that could be used as precision timing devices. If a civilization were aware of these space clocks, they could transmit messages by changing the time or modulating pulses in a recognizable pattern, allowing for potential interstellar communication using natural celestial signals. Despite the excitement surrounding these concepts, one major problem remains: the vast distances between stars and the time it takes for signals to travel through space. Even at the speed of light, a signal from our nearest neighboring star, Proxima Centauri, would take more than 4 years to reach us. As humanity continues to explore and develop new technologies, the prospect of successfully communicating with extraterrestrial civilizations remains an enticing frontier in the search for life beyond Earth. Extreme planetary conditions could have a profound effect on the evolution of alien life forms, leading to adaptations that could be radically different from Earth's. These environments may include extreme temperatures, high levels of radiation, high atmospheric pressure, or different chemical compositions, all of which can create unique challenges and opportunities for life. As organisms adapt to these conditions, they can develop specialized traits and metabolic processes that allow them to survive. For example, on a planet with extreme temperatures, both hot and cold, life forms can develop mechanisms to withstand the environment or even thrive in it. On a planet with scorching surface temperatures, organisms can develop heat-resistant proteins and cell membranes. Under conditions of extreme heat, they retain their integrity. Conversely, species living on a frigid planet may develop anti-freeze compounds that prevent their bodily fluids from freezing, similar to some extremophiles living in Earth's polar regions and deep-sea environments. Iron levels can also determine developmental pathways. On planets near stars with strong radiation, life is able to adapt by developing defenses or biochemical structures to repair damage to DNA and cellular components. These adaptations can lead to organisms with strong cellular defenses that allow them to survive in harsh environments. These modifications may take the form of physical armor, special pigments to absorb harmful radiation, or complex decontamination procedures. High-pressure environments, such as in vents or deep ocean worlds, present different challenges. Life in these areas may evolve differently, perhaps acquiring unique body forms that can withstand tremendous pressures. For example, organisms can develop flexible bodies that can cope with the pressing weight of the atmosphere or ocean. In addition, the presence of unique energy sources, such as high-energy chemical reactions deep in the oceans or near hydrothermal vents, could lead to new metabolic pathways not found on Earth. Finally, the planet's chemical environment could lead to life forms with new biochemical compositions. Researchers hypothesize that on planets with large amounts of ammonia or methane, life could evolve to use these substances instead of water, leading to very different biochemical processes. Scientists continue to explore the possibility of life in extreme environments, in the solar system and on exoplanets, which offers tremendous opportunities for evolution. These diverse adaptations to the most complex environments challenge our understanding of global boundaries and expand our understanding of global energy and innovation.